Right, so this is the second part of Unit 5 on dealing with conservation of momentum and collisions. So conservation of momentum basically says that momentum in a system is neither gained or lost, it just changes form. And if we look at two things that hit, the force acting on two balls during a collision forms an action-reaction pair, like Newton's third law. They have equal magnitudes but opposite directions, due to Newton's third law. So if the momentum of ball 1 increases, that means the momentum of ball 2 has to decrease by the same amount. That's the law of conservation of momentum. The total momentum before a collision and after a collision are constant. That's the law of conservation of momentum. And there's no change in the total momentum of the system, no matter how complicated the forces are. The total momentum is conserved. So you have all these objects interacting with each other. They're going to remain consistent. The total momentum is consistent. And internal forces act only between particles within a system. So the total momentum of a system is subject to only internal forces is conserved. So if there's an external force acting on something, then you have momentum change. But if you're looking at the things within a system, as long as the objects within a system are interacting with each other, the total momentum remains constant. It just changes which one has the momentum. So external forces are forces that from agents outside the system, and they can change the momentum. So you have some sort of external force. It can change them. It will change the momentum of the system. All right. So the change in the change in the total momentum is the change in momentum total is equal to the sum of your change in momentums. So the force on the first object times the time it exerted, plus the force exerted on the second one times the time it was exerted, plus the force exerted on the third one times the time it was exerted. Now we're assuming that the time exerted on all of them, since if they're all interacting, if they're interacting at the same amount of time, the time interval will remain consistent. So then you have F net equals total time. So F net is a net force due to external forces. Okay, so external forces acting on these things. So if F net is 0, the total momentum of the system does not change. An isolated system is a system that no external force acting on it. So a closed system again. Okay, so if you have a closed system, the change in momentum is 0. So law of conservation of momentum again, the total momentum of an isolated system is constant. On the law of conservation of momentum for an isolated system is PF equals PI. The total momentums don't change. And the total momentum after an interaction is equal to the total momentum before the interaction. So the momentum before equals the momentum afterwards. Okay. Since momentum's a vector, it can be written for x's and y components. Okay. The final momentums equals the sum of your final momentums equals the sum of your initial momentums. All right, so example. Two ice skaters are facing each other on a frictionless ice. Sandra has a mass of 45 kilograms. David has a mass of 80 kilograms. They push off each other. After the push, Sandra moves at a speed of 2 meters per second. How fast does David go? If you look at this, the two skaters interact with each other, but they form an isolated system. So because of that, the total momentum is 0. Okay. So since the motion is only in the x direction, all we have to do is look at the x components. So Sandra's component is her mass times her initial velocity. Okay. David's initial momentum is his mass times his initial velocity. Both of these are 0 because they're at rest. So up here, there's zero mass or zero velocity with masses. There's no momentum. In order for the conservation of momentum to hold true, it means that the momentum of Sandra's final momentum has to equal David's final momentum. So their final momentums have to be equal to each other because the total momentum of the object is zero. Now, they're equal and opposite in direction because one's going to have a positive velocity, one's going to have a negative velocity. So, solving for df, we get that because mass times df, velocity David final is going to be mass of Sandra times Sandra's final velocity. So we divide both sides by the mass of David, and we get a negative velocity of 1.2 meters per second. So David is moving backwards with a speed of 1.2 meters per second because our momentums are consistent. Our momentum remains constant. So we didn't need to know any details about the force. Just that their momentum is consistent. Okay, and if you think about it, David should be moving slower because he has more mass. All right, so this all depends on the system you're looking at to figure out the momentum change. So for a skateboarder, if we choose to just the person, there is a non-zero net force acting on the system. But if we look at the person and the skateboard, the net force is zero and momentum is conserved. All right, so we're going to look at somebody on a skateboard. So Jack stands at rest on a skateboard. The mass of Jack and the skateboard together is 75 kilograms. His buddy Ryan throws a 3-kilogram ball horizontally to the right at 4 meters per second to Jack, who catches it. What's the final speed of Jack and the skateboard? All right. So Jack's initial momentum is zero. Okay, because he's standing on a skateboard. To calculate his speed after the catch, we need to calculate his final momentum. So the speed is Jack plus the skateboard plus the ball. Okay, so the initial momentum of the system is the mass of the ball times its initial velocity. So the total initial momentum is 12 kilograms times meters per second. So the final momentum of the ball is the same. So the final momentum is 12 kilograms times meters per second. But the mass is 75 plus 3. 75 because it is the boy and the skateboard plus the 3-kilogram ball. So the mass is 78 kilograms. So the velocity of Jack and the skateboard and the ball after the catch is your momentum divided by your mass, so 12 kilograms times meters per second, divided by 78 kilograms, or 0.15 meters per second. That's how you figure out the final velocity of two objects that collide with each other. Okay, keeping in mind the conservation of momentum, that the momentum before a collision and the momentum after a collision have to be the same. All right, so you have things that collide. Now we have the opposite. An explosion is when particles of the system move apart after a brief interaction. So they start together, but they move apart. An explosion is the opposite of a collision. So instead of coming together or hitting together and bouncing apart, these things start together and go apart. So the forces are internal forces, and if the system is isolated, the total momentum is conserved. So the momentum, the system is consistent. Okay, so that the momentum final is the moment, like for a rocket that is releasing fuel, the total momentum of the system remains constant. In this case, the momentum of the rocket going up is going to be equal to the momentum of the gas going down. All right, so we have a gun that shoots a bullet. A 30-gram ball is fired from 1.2 kilogram rifle with a speed of 1.5 meters per second. What's the recoil speed of the rifle? Okay, so again, we're looking at the momentums have to be consistent. At the beginning, your initial momentums are 0 because there's no initial velocities. So that means that the momentum of the rifle going into the left is equal to the momentum of the ball moving to the right. Okay. So the momentums have to be equal and opposite because you have no initial momentum. Okay, the external forces are balanced by the external forces by the person. Okay, thus the system is isolated, and the law of conservation applies. Okay, so the total momentum is 0. All right, you have no momentum beforehand, no total momentum, and no total momentum before, no total momentum afterwards. So the momentums have to be equal in opposite directions. So, because of this, the mass of the rifle times the velocity of the rifle is equal to the mass of the bullet times the velocity of the bullet. Okay, we know the mass of the ball or the bullet, and we know the mass of the rifle. We know the speed of the ball. So you take the division of the masses times the velocity of the ball, gets you your velocity of 0.38 meters per second. And if you think about it, it should be going a lot lower speed because it has a lot more mass. A lot bigger mass of the gun. It should be going a lot slower. All right. Now we have to talk about something called an inelastic collision. So in what's called a perfectly inelastic collision, the objects stick together and move at a common final velocity. Examples of perfectly inelastic collisions are like something hitting the floor, or something like you shoot like a bullet or a little ball and it sticks itself into the wood. They stick together and they move together as one. Okay? That's called a perfectly inelastic collision. They hit and they stick together. Inelastic collision. Okay, so if you put two train cars together, you're going to make an inelastic collision. Okay, when they meet, they couple and stick together. The lighter car has an initial speed of 1.5 meters per second. The collision causes it to reverse course at 0.25 meters per second. We're going to look at the initial speed of the heavier car. So we have these initially. So what we have is we have the heavier car moving to the left, the lighter car moving to the right. When they hook up, they're moving to the left. We're going to try to find the initial speed of the heavier vehicle, the heavier car. Okay. Okay, so we know all this information. We know the initial velocity of the lighter car. We know the mass of the two cars, and we know that's considering it's an inelastic collision, perfectly inelastic collision. They're going to hook up, so their total mass is combined, which means that they all have the same final velocity, which we know. Okay, so the law of conservation of momentum says the momentum before and the momentum afterwards have to be the same. So we know that the two masses combined plus times the final velocity is equal to the sum of the momentums beforehand. So, because of this formula right here, we're going to take this and solve for V2 initial. So to solve for V2 initial, you take the momentum afterwards minus the momentum of the lighter car initially divided by the mass of the bigger object. So we know the total mass, 2 times 10 to the fourth plus 4 times 10 to the fourth is 6 times 10 to the fourth kilograms. We know its final speed as negative 0.25 meters per second minus the mass of the lighter one times its initial velocity, 2 times 10 to the fourth kilograms times 1.5 meters per second, divided by the mass of the bigger one. You solve this and you get a final velocity of negative 1.1 meters per second. Which means that the bigger car then is moving to the left with a speed of negative 1.1 meters per second. Okay, the heavier object started moving to the left. Okay, so this is big because you have to figure out with these inelastic collisions, the one that has essentially the larger initial momentum is going to determine which way the objects go after the collision. So if they hit and they stick together and their momentums are the same, then they don't go anywhere after the collision. All right. So another example problem. 10 kilogram bullet is fired into a 1 kilogram wood block. The block slides 4 meters across the floor. That has a coefficient of friction of 0.2 for the wood on the wood. What's the bullet's speed? All right, so this one, we know that the kinetic friction slows the combination of the block and the bullet to a stop in a distance of 4 meters because it tells you that. The deceleration due to the kinetic friction on the level surface is the coefficient of friction times g. Okay. So the deceleration of the block is 2 meters per second squared. And you can look here. Okay. With the distance of 4 meters and the final velocity of 0, we can calculate the initial velocity of the block to be the square root of 2 times ax, one of the kinematics equations. Okay. Thus, the total momentum of the system right after the bullet hits and before the external forces is 1.01 times 4 meters per second, which is 4 kilograms times meters per second. This must equal the momentum of the bullet before it hits the block, so the initial velocity of the bullet is 4 divided by the mass of the bullet, which is 400 meters per second. This one, you're going to have to look over a couple different times and ask about it in class, and we'll go over it. All right, the last section of the chapter is two-dimensional collisions. So up until this point, we talked about one-dimensional collisions. Okay, and we looked at X collisions and Y collisions. In these collisions, an individual momentum can change, but the total momentum doesn't. We look at total momentum in 2 dimensions. So we have 2 pucks collide on an air hockey table. We can just ignore friction. Prior to collision, puck 1 travels in a direction that can be considered in the positive x-axis at 1 meter per second. Puck 2 travels in the negative y direction at 2 meters per second prior to the collision. After the collision, puck 2 travels 30 degrees above the x direction at 8.8 meters per second. What's the velocity of puck 1 after the collision? And how does the kinetic energy compare to the total kinetic energy? All right, so to solve for the conservation of the x and y components of momentum independently, the initial x momentum is .1 kilograms times 1 meter per second. That's the mass of the first puck times its initial velocity, which is 0.1 kilograms times meters per second. After the collision, puck 2 has an x momentum of 0.8 times the 0.8 because it has a mass. Okay. Its mass is 0.1. So 0.8 is its final velocity. Okay, 30 degrees. So this is your hypotenuse. You have to figure out the cosine to get your x component times your mass of 0.07 kilograms times meters per second. So puck 1 must have a final momentum of 0.03 kilograms times meters per second. Why? Because the first puck had the total x momentum. of 0.1 kilograms. So if the x momentum was 0.1 kilograms, and the total x momentum was 0.1 kilograms, and the second puck got 0.07 kilograms in the x direction, the puck 1 only has 0.03 kilograms times meters per second of momentum in the x direction left. Okay. So because we know the mass of 0.1 kilograms, and we know its momentum divided by mass gets our velocity of the puck 1 after the collision of 0.3 meters per second. So the initial y momentum is negative 2 kilograms times meters per second. After the collision, puck 2 has a y momentum now of 0.8, because it has the velocity, 0.8 times the sine of 30 times its mass, or 0.04 kilograms times meters per second. That's its y component for its momentum. So puck 1 must have a post-collision momentum of 0.16 and a y component velocity of negative 0.16, just as we mentioned above. So the speed of puck 1 is the square root, so 1.6 squared plus 0.32 squared of the square root of that, of 1.6 meters per second. So the direction of puck 1 after the collision, we can figure out the tangent of our momentums to figure out that it's 10 degrees to the right. And kinetic energy is 1/2 mv squared. And because it loses kinetic energy, a perfectly inelastic collision, all the momentum is conserved. But a partially inelastic collision, there is kinetic energy lost. We'll go through practice problems like this in class. All right, that's the end. I would really go through this, draw it out, make sure you can do it. If not, we will solve problems like this in class. And we'll talk to you in class.